Hey everyone, welcome back to UniAssist. Today we're going to cover a crash course on complex numbers. We'll go through the following topics: solving equations using complex numbers, basic proofs, geometric applications, nth roots, trigonometric applications, and finally polynomials. Before we begin, we'll cover some basic definitions on complex numbers. So let's get into it. So complex numbers can be represented in either Cartesian or polar form. And the way we define them in each situation is like this. So in Cartesian we will have the form x plus iy, where your x is your real part and your y is your imaginary part. In polar form it looks something like this: r e to the I theta, where r is what we call your modulus and theta is your argument. If we were to draw a complex number, we would have to do it on the Argand diagram, and the Argand diagram is different to the normal Cartesian 2D plane that we see, because here we've got the real axis, which we call real z, and the imaginary axis, which we call imz. So if we have a complex number of the form x plus iy, it could look something like this, where this is your x component and this is your y component. Here we could say z equals x plus iy. Similarly, if we were to translate this into the polar form, we would say that this is your argument, or theta, and the length of this vector or complex number would be r. One of the most powerful abilities of complex numbers is its ability to solve polynomials, and in particular quadratics. This all stems from the rule that I squared equals to minus 1. Let's see how we can apply this to a real question. So when solving quadratic equations, generally with complex polynomials, you want to use the quadratic formula. So to recall, the quadratic formula goes like this: minus b plus minus root b squared minus 4ac over 2a. So now all we have to do is just sub in the coefficients. So we'll have z1 subscript z2 equals minus 1 plus minus square root 1 squared minus 4 times 1 times 1 over 2 times 1. Simplifying this, we get minus 1 plus minus square root 1 minus 4 over 2, which is equal to minus 1 plus minus square root minus 3 over 2. When solving this conventionally, you'd be a bit stuck here, because what can you do with square root of minus 3? But here is where the rule I squared equals minus 1 comes in. So what we're going to do is sub this inside the square root function. So now we're going to get minus 1 plus minus square root of 3 times I squared over 2. And now we can solve this because we can square root the I squared. So this ends up being minus 1 plus minus I square root 3 over 2. Therefore, my two solutions are z1 equals minus 1 plus square root 3 on 2, and z2 equals minus 1 minus square root 3 on 2. Now we will look at some basic proofs involving complex numbers. There's generally two methods you can go about doing these proofs. You can either take the approach with the Cartesian form, or you can take the approach with the polar form. Sometimes sticking to one approach makes the question quite difficult, so it's good to be flexible and to know when to use which form. Generally, if the question involves adding or subtracting, the Cartesian method is usually the way to go. So for the first proof, we want to show that z minus z conjugate is equal to minus 2i mz. So for the first question, what I'm going to do is let z equal x plus iy, where x and y are some real number and I is my, obviously, the imaginary part. So here I find my z conjugate to be x minus iy, so I simply negate the imaginary term, and now I can just sub into my left hand side. So we'll go left hand side equals z minus z conjugate, and that equals x plus iy minus x minus iy. Here we get the x's cancel out, and I end up getting 2iy, and this you can see is equal to 2i times y, where y is my imaginary term as defined. So to summarize, I can just put this as 2i times mz, and this equals to my right hand side. Therefore we can say that z minus z conjugate is equal to 2i mz. Okay, on to the next proof. We have to prove that z times z conjugate is equal to modulus of z squared. So for this one, I think I'll also go with a Cartesian approach, purely because the algebra doesn't look too complicated. So here we have, once again, we define z as x plus iy, and naturally z conjugate is x minus iy, and here we do z times z conjugate equals x plus iy, x minus iy, and here we get x squared plus y squared. Note that the imaginary terms cancel out, so you're actually left with a purely real term in this situation. And next we can have a look at what modulus of z squared equals to. So recall that in the Cartesian form, the modulus is equal to the length of the complex number. So if I have something like x and y here, using Pythagoras theorem, I know that this length here is going to be equal to x squared plus y squared square root. So if we label this r, say r equals that, which is equal to my modulus of z. So using Pythagoras, this is equal to x squared plus y squared. And then obviously we would take the all squares of that, and we get x squared plus y squared. Therefore you can see that z times z conjugate is equal to modulus of z squared. And the third proof is that we need to show that modulus of z to the n is equal to modulus of z to the power of n. So let's rewrite that. So required to prove that modulus of z to the n is equal to modulus of z to the n. So naturally, sometimes when I see powers and Cartesian form become quite difficult, and it's usually not a good idea to use that, because we're going to be doing x plus iy to the power of n and so forth, which can get quite complicated. So rather, I want to stick to my polar form instead. So with polar form, as I described earlier in the video, we can let our complex number equal r e to the I theta. And now let's start calculating the left hand side. Here we've got modulus of r e to the I theta to the power of n, which is equal to modulus of r to the n times e to the I theta n, and this is equal to r to the n e to the I n theta. And modulus, similar to the Cartesian form, is the length of your complex vector. So that means that this is going to be the modulus. And you can also think of it like, we can apply another rule that we may use, is that modulus of z omega equals modulus of z times modulus of omega. So if we actually apply this rule, we would get something, we would be able to separate out these two elements and do that, and we know that this is obviously just a real number. and this has a modulus of 1, because this is just a complex vector on the unit circle. And now we're going to get just r to the n. That's the left hand side, and the right hand side is equal to, so it'll be modulus of r e to the I theta to the power of n. And just like before, we can split it all out. So we got modulus of r times modulus of e to the I theta to the power of n. And once again, we know that this goes to 1, and this is a real number, so we end up getting modulus of r to the n, which is equal to r to the n. So therefore, we've got z to the n equals modulus of z to the n. And the last proof that we want to use is now looking at arguments. So we want to prove, it's number 4, that arg of z on omega equals arg of z minus arg of omega. So again, my thought process for selecting which approach to use, either Cartesian or polar, is kind of made easier by the fact that we have arguments. So if you have arguments, generally you want to go polar, because if you want to look at the argument in the Cartesian form, you'll be dealing with the tan inverse, which is a lot more complicated, whereas in polar we just deal with the theta value. So let's start by letting z equal r1 e to the I theta 1, and let omega equal r2 e to the I theta 2. So my left hand side becomes arg of r1 e to the I theta 1 over r2 e to the I theta 2. Simplifying this, we get arg of r1 on r2 times e to the I theta 1 minus theta 2. So this is just using some basic indices laws, and we know that this is a modulus, so it doesn't affect our argument, and the argument here is represented by this value there, so we actually just end up getting theta 1 minus theta 2. And we know that theta 1 is the arg of z1, sorry, z, and we know theta 2 is the argument of omega by definition. So these two by definition, and there we go, that's our proof done, and that equals to the right hand side. Another really common use of complex numbers is in the form of geometric applications. This usually comes in the form of plotting particular relationships that are given to us. So for example, in this question we're told that the modulus of z minus I is less than or equal to 2, and the arg of z is between pi on 3 and 2 pi on 3. This can look confusing at first, but once we break it down, it becomes a lot clearer. So what I usually like to do is I like to handle these two things separately. So let's first tackle the first constraint. Generally with this, we can take an algebraic approach as well. We can let z equal x plus iy, and then solve algebraically what this relationship is. This is a safe option and will always give you the correct answer, but if you are confident, you can also do it geometrically. So I'll first do it geometrically, and then we can compare it with our algebraic answer. So if I was to, I guess, separate this out, so we can say this is the algebraic approach, and let's try the geometric approach. So with the geometric, you always have to do a plot. So let's label, and let's label some arbitrary complex number z. So it says that z minus I is less than or equal to 2, the modulus. So firstly we need to identify where I is on our diagram. So I is on the imaginary axis, so it'll be here. So let's label this point I. And let's draw a line between I and Z. So this is technically a representation of the modulus of Z minus I. You can effectively interpret this as saying Z from I, which is a very common approach with vectors, but it can also apply here. So what the question now tells me is that it's saying that the modulus, or the distance, of Z from I has to always be less than or equal to 2. So if we consider the case where we're looking at Z minus I is equal to 2, that means that the distance is a fixed distance, and basically what that tells me, if this length is always 2, that Z has to kind of basically move in a particular shape where the distance is always 2 no matter where it goes. And as you can see, you just draw out a circle, right? So you end up with a circle with center I and radius 2. So if I was to give this an equation, I would get something like x squared plus y minus 1 squared equals to 2 squared. Knowing that in the Cartesian form, my generic form of a circle is x minus h squared plus y minus k squared equals to r squared, where hk is my center and r is my radius. So we effectively solved this without the need to use any form of algebra. But now, just to prove that this is a sound approach, I will use I will sub in z equals x plus iy and solve it algebraically. But before that, we have to take into effect that the question says less than or equal to, not equal to. So what that means is that z can be anywhere within this circle and it will satisfy our constraint. So basically, what the question is describing is a region of space where you're inside the circle bounded by x squared plus y minus 1 all squared equals to 2 squared. So let's tackle it algebraically now. So we got z equals x plus iy, so I just sub that in, x plus iy minus I less than or equal to 2. Simplifying my left hand side, I get x plus I outside of y minus 1 less than or equal to 2. And as we know, modulus is by definition, write this on the side, modulus or absolute value of z is equal to x squared plus y squared square root. So subbing that in, I get x squared plus y minus 1 all squared less than or equal to 2, and squaring both sides, I get x squared plus y minus 1 all squared less than or equal to 4. And as you can see, it matches the form that we got with the geometric approach. So now that I've confirmed the first part of the question, I will draw it out. So here we'll have, it's always good to do nice big drawings to make everything clear. So you got mz, so my center is at 0, 1 and my radius is 2. So let's just extend out this upper limit here. So my upper bound here will be 0, 2, and here will be 0, minus 1, and it looks something like this, and it's described basically by the region inside, so like that. And I would label this as x squared plus y minus 1 all squared less than or equal to 4. The next part of the question is tackling the argument restriction. So now we've got that the arg of z is between pi on 3 and 2 pi on 3. As mentioned earlier in the video, your argument is by definition the angle from the positive real axis. So if we say theta, that's theta. So this is the angle from the positive real axis in the anti-clockwise direction. So if I were to draw arg of, so let's try drawing arg of z equals pi on 3. So recall that z is once again an arbitrary complex number, but that is centered at 0, 0. So you can think of this as arg of z minus 0 plus 0 I equals pi on 3. So if we were to draw this, that would mean that the argument of z from the axis is equal to pi on 3. So it'd be some value like that. And then if this was equal to 2 on 3, the angle would simply double, and you would get something here where this is equal to 2 pi on 3. Combining these two pieces of information, we're actually going to get a particular range. So if I was to redraw this properly, this is my real z and mz. We got z in the middle here, and the argument of that is, so remember we have to use dotted lines because we're dealing with less than or equal to, or less than and greater than. So this will be like that, and that'll be like that here, where this is pi on 3 and this is 2 pi on 3. Okay, so the next section now is to combine the two pieces of information or restrictions we have. And the next thing to note is that we've got a AND condition. So what AND means is the same as this, which means intersection. So basically, the final answer will be the intersection between the first restriction and the second restriction. So I'll start drawing them on the same diagram. So I'll do this one in red. So we're going to have here, we're going to have this angle of, oops, should be dotted, pi on 3, and this one will be 2 pi on 3. And our final answer will be the region that satisfies both. So recall that for this one we wanted everything between the two, so it would have been this region here, and in this case I'll use a different color. We want this part here. So in effect, our final answer is going to be where we've shaded twice. So I'll just highlight where that's going to be. So the final answer to this solution will be everything that's within these two regions. And it's important to also note that the points of intersection, which are these two, are also quite critical generally in a question, because to have them as solid lines, you would need both conditions to be satisfied. However, we cannot satisfy the dotted line condition, so it will have to be open circled. So if we were to give a final answer combining everything we've just done, we would have this as the solution. So we would have the pi on 3, 2 pi on 3, and then we would have a sector from that circle. This is 0, 2, this is pi on 3, and this is 2 pi on 3. So our answer would be the region inside here, excluding the boundaries.